welcome to the lecture of Kinetics of step growth polymerization, self-catalyzed polymerization and external catalysis under the head of polymer reaction engineering. Now, before we start, let's have a brief look about what topics we covered previously. We discussed about the brief outlook of step growth polymerization with the help of certain commercially important polymers. We discussed about the basic property of step growth polymerization process under the edges of melt polymerization, solution polymerization, interfacial polymerization. We discussed about the emulsion polymerization and solid state polymerization both. Now, apart from this, we discussed the reactivity of functional groups. Now, in this particular chapter, we are going to discuss with the kinetics approach of step growth polymerization. Then we will have a discussion about the self-catalyzed polymerization based on the experimental observation as well as the reasons for non-linearity in third order plot. We will have a discussion about the external catalysis of polymerization. Now, let us have a look about the kinetics of step polymerization. Usually it is imperative to understand how reactions proceed over time. Now, this information can tell us about the time it takes for a polymer to reach to an optimum length that is related to the chain of that particular polymer. Now, let us have a look about the kinetics of step polymerization. It is imperative to understand how reactions proceed over time. Now, this information can tell us about the time it takes for a polymer to reach an optimum length so that it can acquire the appropriate property as desired by the process. Now, just as kinetics can provide insight into the other reaction mechanism, it can also provide the insight into how the polymerization occurs. Now, let us consider the polyesterification of diacid and diol to illustrate general form of the kinetics of a typical step polymerization process. Now, it is quite simple that the esterification is a well known acid catalyzed reaction and polyesterification follows the same course. Now, the reaction involves protonation of carboxylic acid followed by the reaction of protonated species I which with the alcohol to yield any kind of ester. Now, you can see here that how we explain the kinetics of this step polymerization with the help of these three mechanisms. Now, see all acid or alcohol species like monomer, dimer or enmer in the reaction mixtures are indicated by 1 and 2 like here you can see over here. Now, since polymerization often takes place in organic media of low polarity, species 1 and 2 they are shown in the form of this is 1 and 2 they are shown in the form of their associated ion pair. Now, A is the negative counter ion derived from the acid HA. The polyesterification reactions are equilibrium reactions and therefore, you need to address the things associated with the equilibrium criteria to have this type of a reaction. Now, considering the practical viewpoint of obtaining high yield of high molecular weight products, such polymerizations are run in a manner so as to continuously shift the equilibrium in the direction of the polymer. Now, this is accomplished by removal of water that is a byproduct of a reaction species in 2 as shown in the figure. The kinetics of polymerization under these conditions can be handled by the considering the reaction in equation number 2 and 3 needs to be irreversible in this particular slide. Now, the rate of step polymerization can be conveniently expressed in terms of concentration of a reacting functional group. Thus, the polyesterification can be experimentally followed by titrating the unreacted carboxylic group with a base. Therefore, sometimes when we need to find out the rate of polymerization RP, this can now be expressed as the rate of disappearance of carboxylic group that is sometimes referred as dCOOH upon dt. Now, for the usual polyesterification, the polymerization rate is synonymous with the rate of formation of species 2, and that is the K4 is usually vanishingly. Now, for ease of this, again I am showing the mechanism of that particular reaction over here. Now, here you see that there are the K4, K3, these are the rate constants for forward direction and backward direction, and sometimes when we talk about the irreversibility etc., then we need to address the equation 2 and 3 in that case. So, when we talk about the reaction run under the condition usually that prevails under the equation number 2 and 3 towards the right, the K1 and K2, K5, they are the large as compared to K3. So, the general procedure for handling a reaction scheme with the characteristic described, this can be used to obtain an expression for the reaction rate. Now, let us have a look about the rate of polymerization. So, the rate of polymerization is given by Rp, that is equal to d COOH upon dt, and Rp is referred as K3 if you recall those equation, C plus OH. This can be represented as equation 4. First three equations are represented in that particular mechanism. Now, where this COH and OH and C plus OH twice, they represent the concentration of carboxylic, hydroxyl, protonated carboxylic groups respectively, and the concentration terms are in the unit of moles of the particular functional group per liter of solution. Now, this particular equation which we represented in the previous one, that it is inconvenient as the concentration of a protonated carboxylic group is not easily determined experimentally. So, one can obtain a more convenient expression for a rate of reaction. Now, if we substitute, if we have a substitute for C plus OH twice from the equilibrium expression for the protonation reaction, then we can have this particular equation like K is equal to K1 upon K2, that is C plus OH upon COOH HA. This can be represented as equation number 5. Now, if we combine both the equation 4 and equation 5, for convenience again I am writing the equation number 4, that is Rp is equal to minus d COOH upon dt, or Rp is equal to K3 C plus OH. This is equation, this was our equation number 5. Now, if we combine both these equations, then we may have minus d COOH upon dt is equal to K3 K COOH OH. That is equation number 6. So, the two quite different kinetic situations arises from this equation number 6 depending on the identity of HA, that is on whether a strong acid such as sulfuric acid or para-toluene sulfonic acid is added as an external catalyst. Now, one of the most important properties in the condensation polymerization is the polymer's molecular weight. As we discussed that polymer's molecular weight play a very vital role in all kind of property determination approaches. So, consider a linear step growth polymerization of AB type here in this particular figure. Let A refer to the hydroxyl group and B refer to the carboxylic acid group, so that a polyester is formed and the polymerization reaction can be represented like this. Now, in step growth polymerization, it is common to use the symbol P rather than X to refer the conversion of limiting functional group. Now, as the conversion is equal to the probability that a particular functional group, say sometimes hydroxyl group, OH group, in the original reaction mixture, it has reacted with another functional group, sometimes carboxylic group like COOH. Therefore, the probability that a random molecule will have a chain length n would be P Pn is equal to Pn minus 1 into 1 minus P. Let us refer as this particular equation number 7. So, the consumption of exactly n monomer to form the this polymer chain requires n minus 1 independent chain linking reactions. Now, each will probably with the probability P, and also that one hydroxyl group, that is the one at the end of the resulting molecule. So, this has not been consumed and which has the probability of 1 minus P. So, the distribution in the previous equation, that is equation number 7, is called the most probable distribution, or sometimes referred as MPD or Schulz-Flory redistribution. Now, the probability Pn, usually it corresponds to the mole fraction of nmer, that is sometimes referred as Xn. Now, as conversion increases, sometimes we say that P tends to 1, the mole fraction of small molecules decreases and the mole fraction of larger molecules increase, but the species with the largest concentration is always the monomer. So, that the number CLD, that is referred as a chain length distribution, or sometimes mathematically we can represent as equation number 7, is a decreasing function of chain length. Now, we can utilize this particular equation number 7 to develop an expression of the weight chain length distribution for this AB type of polymeric system. So, in that case, let us have that n be the total number of molecules remaining at conversion P, and n naught be the initial number of monomers, then n is equal to n naught 1 minus P, and the mole fraction of n mer can be represented as, now it can be represented as Xn n naught 1 minus P. Now, since this Xn is equal to Pn, and that is equal to P to the power n minus 1 1 minus P, that we have already represented. So, the number of moles of n mer can be represented as Nn is equal to n naught P n minus 1 1 minus P to the power 2, and this can be represented as equation number 8, and this can be represented as equation number 9. Now, if go to the weight fraction concept, and we talk about the weight fraction of n mer, sometimes it is quite useful, then it can be represented as Wn is equal to Nn and Wm upon n naught Wm, and this is n naught 1 minus P square P n minus 1 n upon n naught, or upon arranging, we can write 1 upon 1 minus P square P n minus 1 n, and you can write this as the equation number 10. So, this here you can say the Wm, sometimes the molecular weight of a repeat unit. Now, you may take the assumption that the total mass of repeat unit in the polymer chain is large compared to the mass of end group. So, whatever end group is here, you can say that the total mass of this particular polymer chain is larger than the mass of this end group. So, sometimes we may talk about the number average degree of polymerization and referred as dPn. It is again quite important in case of the step growth polymerization. So, the number average degree of polymerization, this can be represented as dPn is equal to summation n is equal to 1 to infinity nxn, n is equal to 1 minus P n P n minus 1, or this is 1 minus P 1 plus 2 P plus 3 P square plus and so on, or this can be represented as, if we adopt the proper mathematical tool to represent this degree of polymerization, it can be represented as 1 minus P upon 1 minus P square, and that is 1 minus p. Now this can be represented as, let us say, for the ease of calculation, we can represent that equation number 11a. Now the weight average degree of polymerization, the dPW, because previously we talked about the number average degree of polymerization. Now sometimes the determination of weight average degree of polymerization, dPW, can also be a very important thing, and this can be calculated easily from the number and weight chain length distribution. So it can be represented as dPW, that is equal to n is equal to 1 to infinity nwn, n is equal to 1 to infinity 1 minus p square n square p n minus 1, or 1 minus p square 1 plus 2 square p plus 3 square p plus and so on, and this can be represented as 1 plus p upon 1 minus p, that is our equation number 11b. Now the polydispersity index is usually referred as PDI is equal to dPW upon dPn, and in that case it is 1 plus p. Since p is very close to 1 for linear, then the high molecular weight step growth polymerization or polymers, the polydispersity index is very close to 2. Now this equation 11a and 11b, these two equations indicate that for this simple step growth polymerization, the molecular weight averages can be calculated easily from the conversion, and that the conversion P must be very close to 1 to obtain the high molecular weight polymer. So this is a particular important thing is need to be look into while considering the kinetics of step polymerization. Now sometimes when we talk about the self-catalyzed polymerization, then in the absence of an externally added strong acid or diacid monomer acts as its own catalyst for the esterification of reaction. That means sometimes the reactant itself, sometimes the product being developed in due course of a time within the reaction mass, they can act as a catalyst for the polymerization reaction. They are clubbed under the head of self-catalyzed polymerization. For this case, HA is replaced by COH, and the equation, my original equation 6, this can be written in the usual form like this: minus D COOH. It is quite evident that why we are putting the minus sign, because it is being consumed in the course of reaction. Then it can be OH. Let us represent that as equation number 12. Now sometime here the K and K3, if you recall the original reaction condition, they have been combined into the experimentally determined rate constant K. So that is the slight modification, because it is a self-catalyzed type of polymerization. Now in this equation, this particular equation shows the important characteristics of self-catalyzed polymerization. Usually the reaction is the third order overall, with a second order dependency on the carboxylic concentration. Now the second order dependency on the carboxylic concentration is usually comprised of two first order dependency, one for the carboxyl as the reactant and one for the catalyst. So remember here the carboxylic group act as a twofold. One is acting as a reactant and another one is acting as a catalyst. So there are two type of a dependency in the first order reaction you need to consider. For most polymerization, the concentration of two functional groups are very nearly stoichiometric, and my previous equation number 12 can be written as minus d m upon dt, that is k m cube, that is let us say that this is my equation number 13a, or minus d m m cube, that is equation number K. That is equation number 13b. So, you can represent these two equations. Now, where this concentration M is the concentration of hydroxyl group or carboxylic group, and integration of this particular 13b, this yields the 2 kT is equal to 1 upon m square is equal to 1 upon m naught square. That may be represented as equation number 14. Now, here m naught is the initial concentration at time t is equal to 0 of hydroxyl or carboxylic group, whatever you like. Now, it is convenient at this particular juncture to write equation 14, which we discussed over here, in terms of extent of a fraction of a reaction P defined as a fraction of hydroxyl or carboxylic functional group that has reacted at time t. Now, sometimes P is also referred to as the extent of a fraction of conversion. The value of P is calculated from a determination of the amount of unreacted carboxylic group. So, the concentration M at time t of either hydroxyl or carboxylic group is can be given by M is equal to m naught minus m naught P, or this is m naught 1 minus P, that is equation number 15. So, if we combine the equation 14 and 15, then we may have 1 upon 1 minus P square, that is equal to 2 m square kT plus 1, that is equation number 16. Now, sometimes the experimental observation plays a very vital role. Now, this equation 16 indicates that we try to plot graph of 1 upon 1 minus P square versus T, this should be linear. So, at a first glance the plot does not appear like this, it does not appear to exactly follow the relationship. So, the experimental points deviates from the third order plot in the initial region like this. Here you can see this is the third order plot of self-catalyzed polyesterification of adipic acid with the diethylene glycol. We have referred this figure from George Odion. Now, if we see that it deviates from third order plot in the initial region below 80% conversion, and the later stage about 93% conversion can be achieved over here, you can see. So, these deviations sometimes led to the various worker to suggest alternate kinetic expression, usually based on either one or half order dependencies of the reaction rate on the carboxyl concentration, that is 2 and 2.5 order dependencies. So, when we consider all those things, then we may have another approach when we talk about these second and half order things. Then we may write this d COOH upon dt, that is K COOH. Let me write that this is equation number 17a, and minus d COOH upon dt, that COOH 3 by 2 OH, referred as 17b. So, when you see that the experimental rate data fits in equation 17a well only in the region between 50 to 86% conversion, with an excessively poor fit about 86% conversion. Now, on the other hand, a plot according to the equation 17b fits reasonably well up to about 80% conversion, but deviates badly above that point. So this point need to be, and that's why the experimental data also play a very vital role when we talk about the validity or validation of those mathematically derived equation. So neither of these two alternative kinetic plots based on equation 17a and 17b come close to being as useful as the third order plots. So the third order plot fits the experimental data much better than does either the of the other at the higher conversion. The fit of the data to the third order plot is reasonably good over a much greater range of the higher conversion region. So the reason of high conversion is of the prime importance, since high molecular weight polymer is obtained only at high conversion. So if your target is to have to obtain the high molecular weight polymer, then you need to look this particular aspect. So from the practical point of view, the low conversion region of the kinetic plot is of having very little significance. Now sometimes people may talk about that what should be the reasons for non-linearity in the third order plot. So the non-linearity, they are not inherent characteristics of the polymerization region. There may be certain low conversion reasons. So P.J. Flory in 1953, he attributed the non-linearity in the low conversion region to the large changes that take place in the reaction media. Now the solvent for the reaction changes from an initial mixture to carboxylic acid and alcohol to an ester. So the reaction rate constant increases with decreased solvent polarity, since the transition rate is less charged than the reactant. So it has also been suggested that the excessive or extensive association of both the diols and diacid reactant in low conversion region, they lowers the reaction rate by effectively decreasing the concentration of the reactive species, and that is a free or sometimes unassociated OH or COOH group. So the low conversion region usually fits an overall 2.5 reaction order. It is usually better than it does with the third order reaction. Change from 2.5 order to third order as the reaction medium becomes less polar is compatible with a change from specific yield. Sometimes protonic catalysis to the general acid catalysis. The proton concentration is relatively high, and H plus ion is more effective catalyst than unionized carboxylic acid in the polar and low conversion region. Now, if we again go back to the my equation number 1, 5 and 6, especially with respect to HA, usually is replaced by H plus. So, the reaction rate becomes the first order in each carboxylic and hydroxyl group and H plus. So, the proton concentration may be usually given by H plus is equal to KHA, because we have replaced this one to the power half. This may be represented as my equation number 18. So, if we combine equation 6 previously discussed and equation 18, this may yield minus d COOH upon dt, that is K3 KKHA to the half COOH 3 by 2 OH. That can be represented as equation number 19. So, here you see that KHA is the ionizing constant for the carboxylic acid. Now, another problem is the very high concentration of reactants, those present in the low conversion region, and that is again a most trivial problem. So, yet another possibility for the non-linearity in the low conversion region is the decrease in the volume of the reaction mixture with conversion, that is due to the loss of one of the product of reaction, as we attributed that water in the case of esterification. that's sometimes referred as a condensation product. Now, it is unclear whether this effect alone can account for the nonlinearity in the low conversion region of esterification and polyesterification. Now, let us talk about the high conversion region. Now, the non-linearity usually observed in the third order plot in the final stage of polyesterification is probably not due to any of the reason which we described earlier. Since the reaction system is fairly dilute and relatively low polarity. Another possible reason for the observed non-linearity is an increase in the rate of reverse reaction. The polyesterification reaction is an equilibrium reaction, and it often becomes progressively more difficult to displace the equilibrium to the right, now sometimes towards the polymer, as long as we go for the higher conversion or conversion increases. Now, this may be because of the greatly increased viscosity of the reaction medium at a very high conversion. Now, the large viscosity increase decreases the efficiency of water removal and sometimes may lead to the decrease in the reaction rate with increasing conversion. Now, sometimes we need to address the issues attributed to the external catalysis of this step growth polymerization. The slow increase in molecular weight was mistakenly originally thought to be due to the low reactivity of functional groups attached to the large molecule. Now, it is however simply a consequence of a third order kinetics of direct polyesterification reaction. The realization of this particular kinetic situation sometimes led to the achievement of high molecular weight products in reasonably reaction time by employing the small amount of externally added strong acid sometimes as a catalyst. So, that is the external catalysis type of scenario. So, under these conditions, let us again refer to the previous equation number 6. HA in that particular equation, that is the concentration of the catalyst. Since this remain constant throughout the course of the polymerization, so we can write the equation number 6 in a slightly modified way, that is minus d m upon dt, that is k dash. Now, sometimes you may refer this as the equation number 20. Now, here the various constant terms in equation 6 have been collected into the experimentally determined rate constant k dash. Now, this particular equation which we discussed over here, this applies to the reaction between the stoichiometric concentration of a diol and diacid. So, if we integrate the equation 20 which we discussed, this can give us another approach like that k dash t is equal to 1 upon m upon 1 upon m, and then this is m naught at t is equal to 0. That may be equation number 21. Now, if I try to combine the equation number 21 and equation number 15, this may yield to give that m naught k dash t equal to 1 upon 1 minus p minus 1. That may be referred as equation number 22a, and xn is equal to 1 plus m naught k dash t. That may be represented as equation number 22b. Now, the concept of functional group reactivity independent of molecular size has been highly successful in allowing the kinetic analysis of a wide range of polymerization and reactions of polymers. So, its validity, however, may not always be quite rigorous at a very low or a very high conversion. So, in this particular segment, we discussed about the kinetic analysis of step growth polymerization with the help of various approaches, those who are extensively being used. Maybe you can call that some self-catalyzed polymerization, some sort of an external catalyzed polymerization, and we gave the due respect to the low conversion as well as the high conversion. Now, if you wish to have further more discussion, we have enlisted several references for your convenience. You can refer those references and you can enhance your knowledge. Thank you very much.